They have been fabricating really, really big optics. But one day, they decided to go smaller, really smaller. And just for fun, they started fabricating the tiny telescope. And they uploaded a video on YouTube, and it got a lot of interest. And that's why they decided to found the tiny telescope in 2024, almost 2 years ago. One of the founders is actually here with us, Rick. So if you have any technical questions, just feel free to reach out. But how does it work? So what is the tiny telescope? The tiny telescope is a telescope folded in one single piece of glass, of fused silica, where all the refractive and reflective surfaces are in this piece. So we have the light that enters from the left, then it travels inside the fused silica until it hits the primary mirror. Then we have the secondary mirror, and before the light exits the telescope, we also have a field corrector. Before reaching the focal plane, there's also some room for filters or windows or whatever is needed. Here you can see the design of Zemax, and you can see we are able also to put the baffles inside the glass. And as you can imagine, being this telescope really compact, then the surfaces that we have are extremely spheres, and they're really challenging to fabricate. And also, since the light is traveling inside the glass, then the accuracy we need to fabricate these surfaces with is 6 times higher than a normal telescope focusing in air. But there are, so the material that we use, that I said, is fused silica, which has a quite good transmission from the UV to the shortwave infrared. We can also use some special types of fused silica to extend the wavelength range, either like to longer wavelength or shorter wavelengths to the UV. And we are currently also exploring some other new materials to extend the operational range to longer wavelengths. The fact that we have one single piece, of course, has a lot of benefits. First of all, it has, of course, a low swap. So it's really compact and light, and you can take it basically anywhere. It is diffraction limited, and we don't have a spider holding the M2, so it doesn't suffer from diffraction spikes. It's temperature insensitive, which means that it can operate from cryogenic temperature up to extremely hot temperature, always delivering sharp images. It is really robust against radiation and vibration. And since it is only one piece, of course, once you have fabricated, you don't need to align it and do much testing. So it becomes also more cost effective. What you see here is one of the 2 models that we have at the moment. We also have a live demo downstairs, if you have already been to our stand. This is a 40 millimeters aperture with a focal length of 240 millimeters. And to have an idea of the field of view of such telescope, it is roughly the size of your thumbnail at arm's length. So for example, here, if you look at this broadcasting tower at around 1 kilometer's distance, we can compare the images taken with a phone, for example, or a Canon camera. And on the right, you have the image taken with a tiny telescope, and you can see really the sharp details of the tower. This is another picture that we have taken at our facility of the radio dish that we have there at 100 meters distance. And you can see we are able to see even the mesh of the dish, of this radio dish. Here's a simulation of what you can achieve with this telescope at different distances, or in the case of a satellite, altitudes. For example, on a LEO orbit at 500 kilometers altitude, you will be able to achieve a resolution of around 5 or 6 meters. Or for drones application, for example, at 100 meters distance, a resolution of 1.5 millimeters. So this is a simulation of what you'll be able to see at 500 kilometers altitude. This is a view of Rotterdam. The field of view would correspond to a 25 by 25 kilometers area. And as I mentioned, the resolution we will be able to achieve is 5 meters. So we can see the boats on the canals. So we are able to predict what the telescope would see together with a sensor by taking a high-resolution image with an infinite resolution, and we do the convolution with the point spread function of our telescope, and we can then predict what the telescope would see. But then we realize then we can actually measure the real PSF, the telescope, and we can predict better what it would see. So this is a theoretical PSF for different wavelengths. In this case, we simulate the PSF by introducing some aberrations of the telescope. And we can use that PSF with the aberration to do the convolution and predict what the telescope would actually see. But then we also thought, okay, we can also do the opposite. So if we have the image that the telescope took, we can do the deconvolution to improve the contrast of the image. So you can see on the left, the really high resolution image. In the center, what the telescope would see with some noise also introduced. And on the right, the image we're able to retrieve after the deconvolution. This is the other model that we have of the tiny telescope, the smaller one. This has an aperture of 25 millimeters and a focal length of 125. And this is a picture taken with this telescope. On the right, a picture taken with a standard camera, where you're not even able to see the person climbing the wall. But on the left, we have the picture taken with a tiny telescope, and we are able even to see the shoes of this person climbing. Here's a summary of the specifications of these two tiny telescopes. As I said, the 25 millimeters aperture and the 40 millimeters aperture. And an interesting thing is also that they are really light, because the smaller one is only 30 grams, while the bigger one is 150 grams. And of course, the fact that they're really light and compact makes them a really good candidate for a platform such as the one of the PocketQube. So far, I've been talking about space applications because that's our main goal. So Earth observation cameras, but also star trackers. And we're also exploring laser communications now. But apart from all the space applications we have many on-ground applications. We started now a project in medical imaging for the eye inspection, but also, as I mentioned before, drones, or one day even mobile phone cameras. This was our really first test for laser communication, where we were able to send visible light with our bigger telescope, the 40 millimeters one. And you can see here this test was successful. At the moment, we have 4 locations in the Netherlands. Nova, that I mentioned at the beginning, is where the production is. And we will have a new sales department starting from April next to Estec at the ESA Incubation Center in Noordwijk. And even though the official team is made of only 7 people, there are more than 20 people working on Tiny Telescope. This is the picture that we took at the opening of our facility, the one that we call the Tiny Factory, because it's actually a really tiny factory. But we're able now to produce a few hundreds units per year. So we are increasing the production. And on top of that, we also have many partners in the Netherlands, such as ESRO, the Space Research Organization of the Netherlands, where we can test our products. But this is one of the many that we have. 2026 actually will be an exciting year for Tiny Telescope, because we will have our first launch this December. As I mentioned before, we have this new project on medical application for the eye inspection starting soon. We are planning to do some drone tests as well for our on-ground application, and we are also working on new patents for different technologies. Thank you for your attention.